All right, guys. Today we're doing the shell method homework. So let's talk about what the shell method is before I even do the homework. Again, the mathematics of it is pretty fair and simple, but the visualization of what exactly is happening is different. So we'll start with number one, though. Okay. So what is happening? So technically, you can change this to be equal x and do the distant washer method from yesterday or from our last lesson. So you could technically change it to the equal to x and then do all that method like that. What's going to happen though is that sometimes, like in number two, that makes it extremely different and difficult to do the distant washer method. Like you have to do two separate integrals and you have to set it up correctly. You have to think about the bounds, and that's tough. So instead, what we could do is a shell method. Now, what exactly is a shell method? Normally, the distant washer method is you make a cylinder around the x-axis, or it could be the y-axis, but you make an x-axis, and you make your cylinder by just changing the length of the radius of that cylinder, depending on how big or how small the gap is between the curve. So usually that's our distant washer method. What's this shell method is saying, what if we made, it's the x-axis like this, what if we made our cylinders like this, like if we took our measurement like this. So instead of making the volume of the cylinders, we found what the tips or that surface area of the cylinders are, okay? So we're looking for the surface area of the cylinder when we make our cylinder. And considering this is the y-axis, we're kind of making it like a cylinder here, a cylinder here, a cylinder here. We're moving up and up. So let's visualize what we're actually finding the area of or the volume of. So like you have your cylinder, let's say right here, and you're trying to find, like, it's rotating. Literally, you're trying to find the edges and how big the edge is. And then sometimes the edge is really small, sometimes the edge is big, sometimes the edge is going to be like this one, it would be like to start off small, gets wide, and then start off small again, and end small, I should say. So you're trying to find this outside the surface area. Now, this would be like the label of your soup can. This is the surface area of the infinitely small cylinder. So when you take the surface area of the, like the label side of a soup can, and you flatten it out, it becomes a rectangle. So what we're going to use as a formula is essentially length times width. And then one part of it's always going to end up being the same, but we're going to try to find the length of these squares, the width, or the height, I could say, of these squares, these rectangles, I should say. And then over dx. So we have the infinitely small one. So we just keep adding all the small rectangles. So we got to find the area of these rectangles. So let's talk about this one. This is the length of the rectangle. Let me go back to the cylinder. Depending how wide open your cylinder is how wide your surface area is, or your length. So the outside of the circle decides the length of your rectangle. Now, the outside measurement of the circle, which I literally just taught to my geometry class like 2 days ago, is the circumference. So every time we need to find the circumference of the length, right? The length will equal the circumference. So we're going to use and find the circumference, which the formula is, ignore that one, is 2 pi r. That's 2 pi r. Now the question is, there's no r in our equation, so what is r? Well, r is the distance between the center of your circle and how far away the edge is. So the center of your circle is the y-axis. The center of your circle is your y-axis. So the farther away you get your y-axis is measured by a simple variable, is x. Like if you're at 2x, you're 2 units away from your y-axis. If you're 10x, you're 10 units away. So instead of it being 2 pi r in our equation, it's simply 2 pi x. So that first part is always going to stay consistent, by the way, in the shell method, because the radius is just always going to be dependent on the x variable. So it's 2 pi x, which is up here, okay? So we just found our length of a rectangle. Now we need to find the height of the rectangle. Well, the height of the rectangle gets bigger and smaller depending where you are. In the beginning, at like point, I zoom this in even more now, but like 0.001, it's a really small gap. But somewhere at like the half point, it's like as big as possible. And then at this, like 0.999 is small, so it varies. Well, luckily, we already done a lot of work of how to measure the size of a rectangle over a varying amount of curves. That's integral. And our integral is going to be our f of x. Now, our f of x, though, is in between two curves, so we're going to have to subtract these two equations. So we found our length, and we found our height here. And again, we're just finding a bunch of small rectangles across a certain distance. So now we can set up our integral. So our integral, let's see the stopping points. It seems like it intercepts, and we're using dx, so we're going to do the x or it hits the x-axis. So at 0, 1. So our integral goes from 0 to 1 to pi x, that's my length, times my height. My height varies depending on where I am. So it's going to be f of x. Now, the distance between these curves is the top curve subtracted by the bottom curve. The top curve in this case is square root x plus 4. So the square root of x plus 4 minus the whole bottom curve, which happens to be the parabola, which is 2x, x squared plus 4. So x squared plus 4. Close that parenthesis for this piece right here. Close the big parenthesis because this is this whole thing, which I'm underlining in blue, is my height. This whole thing is my height. And then you're taking your infinitely small distances, which is dx. Okay? 2 and pi are constants, so you could put that on the outside. See if I could just be cheap and just do this. There we go. So 2 and pi is going to be on the outside. And then let me just move this a little closer. And then in here, you could distribute and solve and do the antiderivatives, but you're free to use your calculators. So right here should be our setup for the equation. And let's just check if I'm off with my assertion. 2 pi from 0 to 1, x, subtract these two, dx. So the setup is a length times width. The length is always, always, always in the shell method, 2 pi x. So that's like a constant, essentially. The only thing that really changed in this question is where you start and stop. So your beginning and your end. Your endpoints of your integral. And then your function, so your f of x. So that's your answer for number 1. And that's how you create the answer for number 1. So let's go back here. Oh, what the? What is this? Just want to move it. Whatever, I'm just leaving it. Okay. All right, let's go to number 2. Number 2, they have to give us their x is 0 and x is 4, simply because they want us to stop at 0 and 4. Technically, do these intercept? They intercept eventually. They intercept at 49, but they don't want us to go all the way to 49. They just want to go to 0 and 4. So we got to find the area or the volume projected that is rotated around the y-axis. So we're going to use the shell method again. So the shell method in this one, the first thing that's always, well, first let's find the bounds of our integral. So in terms of x, it seems that it stops from 0 and it goes to 4. So our integral is going to go from 0 to 4. Our length, the length of these labels or these shells is going to be 2 pi r, or 2 pi, because we're not going to use r, is how far away it's from the y-axis, which is just the variable x. Parenthesis, times the height, and the height varies between the distance of the two curves. So the top curve seems to be 7, and the bottom curve seems to be square root x. So it's going to be 7 minus square root x, close the parenthesis, dx. And then again, our 2 pi is nice constant, so we can move that in front. So 2 pi from the integral 0 to 4, x, parentheses, 7 minus square root of x. Okay, so we set it up. The rest is history. You guys could use the calculator or you could use your antiderivatives. I didn't tell you to do homework at number 3, but I do like to talk about it just because it is an interesting concept. Yeah, oh boy. Let's move this here. Move this here. Okay. So number 3 is just asking you, please do the distant washer method for number 2. Tell me what's different about it. Now, in the red, they kind of describe it a bit. If you were to set up the integral for the distant washer method, you have to do 2 different stopping points because the top of the curve or your y curve is going to be slightly different depending where you are. So notice you have 2 integrals here, y squared dy plus pi from 2 to 7, 4 pi dy. It'll still get you the correct answer, but because this requires 2 integrals, you might consider that a little bit tougher. And then also you have to do, sometimes you'll have an equation that's not easy to convert to x equals, and that'd be a headache. In the Khan Academy one, they did a good example because they picked an equation that's like a real pain in the butt to get it to x equals y, x equals by itself, solve x. So they picked that one on purpose because then it's such a headache to do the distant method that you should be using the shell method. Okay, let's get to the last one. Oh, we're looking at the answer. So number 4, it asks you to actually graph it. And I guess I haven't done those by hand graphing in a while, so let me just try it myself. So the equation is, oh, these are super easy. The equation is x equals 2y. So we got a line from here to 2, and then to 4, and then to 6, and then to 8. And then we got our curve of our parabola at 2x, so that's 0, 0. At 1, it's at 2. Let me use a different color. That's 0, 0, and 1 and 2. So we got our curve like this. Oh, I'm not got a steady hand, but whatever. Imagine that, but better looking. And then we're trying to find the volume wrapped around the y value of the area between here and here. So this area right here. So we're trying to find that greened out area. Okay, so let's do this if we were just solving the problem. All right, we have the integral. And then after you do a couple of these, you know that 2 pi is going to be on the outside. So you can even start off like that. So because I know it's going to eventually pop up there. So the integral of where the x intercepts, which should be 0 and 1. So from 0 to 1 is going to be x. It will be 2 pi x, but I already moved the 2 pi outside. The top curve in this case is 2x. So it's 2x minus 2x minus x squared, close parenthesis, dx. So we set it up and we could solve it.
Still, shouldn't it be 0 to 2? Because don't you start at 1, 1? I think you started at 1, 2.
It is 0, 0, and 1, 2, right? Since we're using the x's, we see where they hit each other.
It's y equals x squared, so aren't the first 2 points at 1, 1 on the graph, not 1, 2?
Ah, thank you. Oh, that's why I don't graph by hand anymore, because I suck at it. All right, let's clear this up. Okay. So assume the red line was straight, right? Because 1, 2, 1, 2, 1, 2. And then the curve is y equals 0 squared. So that's 0, 0. At 1, it's 1. At 2, it's squared, so it's 4. So a little bit better. Okay, thank you, Jared. So, oh my gosh. But still. All right. Again, that's why I always suggest use a computer just to graph for you. So instead of your bounds being 0, 1, it's going to be bounds from 0 to 2. Thankfully, the equation on the m side doesn't change that much, or it doesn't change at all. So, I mean, you could even do this by hand. 2x squared minus x to the cube with 2 pi on the outside. Integral 0 to dx. Antiderivative, so that's 2x to the third over 3 minus x to the fourth over 4 from 2 to 0. 0 is going to be irrelevant, so you could just plug in 2 if you really wanted to. All that times 2 pi. Plug in a 2 here, 2, 4, 8, 16 over 3. Minus 2, 4, 6, 2, 4, 8, 16 divided by 4 is 4. So I'm going to make that 12 over 3. So that's 4 over 3 times 2 pi. So 8 pi. 8 pi over 3. It's always good to sometimes do it by hand to see how rusty you are. But 8 pi over 3 is my answer. Luckily, I got that one right first try. I think that's all the questions I asked you on the homework. So we're good to go. Any questions, you could ask them. If not, you're free to go.
Thanks, Mr. T.
Thank
Thank
you.
you.
All right, see you around, guys, okay?